Physicists are always endeavoring to represent everything in the world as numbers. Scalars can be represented as single numbers, such as the mass of this stone or the height of this tree. But when we want to describe the velocity or inertia of this bird, we fall into trouble using single numbers. Luckily, higher dimensional quantities, tensors, can be described using multiple numbers. If quantities can be expressed as single, tuples, or sets of numbers, does that mean tensors are just set of numbers? To make it clear, let's start our consideration with first-rank tensors, vectors. We know that a three-dimensional vector consists of three numbers, but does that mean an arbitrary set of three numbers, say your mom's and your dad's favorite number, makes up a vector? Think about that for a second. Let's take a closer look at vectors. The velocity of these birds is exactly the same thing to both the man on the left and me on the right, of course. However, from my point of view, I will set up a coordinate like this to give out three numbers as the components of this vector. But the man may set up a coordinate with the x direction pointing to a different angle and give out three totally different numbers as mine. Wait a minute, does that mean a vector can be written as two totally different sets of numbers? Actually, a vector can be written as infinite three tuples. This only depends on the coordinate systems one use. We may rotate, stretch, or mirror the coordinates so the value of each component will change, but the vector itself stays still. Coordinate transformations, the change of basic vectors, compensate the change of components. So it turns out that the three tuple defined above, whose component doesn't change as a coordinate transforms, is not a vector. So to define a tensor, we need the information about its transformations. There are other coordinate transformations as well. If the angle between axes become oblique, there will be two ways to write a vector as a three-tuple, and each component can change between the covariant and contravariant forms. Transformations between Cartesian, spherical, and cylindrical coordinates are also used frequently in electrodynamics. So this explains why the angular velocity, which seems like a vector, but reverses its direction if mirrored, is called a pseudovector. Also, if you go fast enough, your position vector and time will change according to special relativity. But the components will form a four-dimensional vector, which remain unchanged under the Lorentz transformation. Zeroth-rank tensors, scalars, such as the mass of the mountain, it is the same according to both the man on the left and me on the right, of course. However, another quantity, say the angle between the sun, the mountain, and the observer, depends on the spatial orientation of coordinates and will change under transformation. Thus, it is not a scalar. Now, let's talk about second-rank tensors. The wind blows this tree and make it bend. Consider a tiny piece of wood here. 9 numbers are needed to describe the stretching and slanting of its shape. These numbers are the components of the tensor, but beyond the simple matrix, they change under transformations and compensate the change of coordinate. This is like if we meet some different civilizations from other galaxies. They may use a totally different language system to define a natural object, like the universe. The description is different under different languages, but they mean the same thing. Actually, math defines the quantity, but the physics of nature choose which one to use to describe the world, and it endows this simple quantity a higher level of complexity. And that's why the world is amazing.